Welcome to the Nokia Optical Network Learning Essentials video series from the Nokia Optical Network Certification Program, an end-to-end learning program supporting Nokia 1830 PSS, VWM, NFMT, and WaveSuite-based networks. In this video, we'll show you how to troubleshoot a channel. This video has been created based on the Nokia Optical Diagnostics and Troubleshooting course. Today, we'll troubleshoot a physical channel issue by analyzing the node alarms, the optical power levels, and by confirming the problem with a wavelength tracker view of the impacted channel. Several ways are available to troubleshoot a technical problem. Depending on the type of issue detected, one or more of the approaches shown here can be used to tackle the problem. 1. Check the documentation available on the support portal. Is it a well-known issue? Is it a real issue? 2. Compare the network design provided by the EPT with the current network configuration. Is the actual configuration aligned with the design? Has the initial commissioning been done correctly? 3. Carefully check for alarms, conditions, and logs. Is the problem still present, or has it happened in the past? 4. Check the wavelength tracker information to isolate and establish where the issue is occurring. Is it possible to spot a point of failure in common with several channels? 5. Check for performance monitoring to analyze if the issue is recurring, its frequency, and the thresholds crossed. Are the values retrieved aligned with the expected operational parameters? For the specific problem we'll be analyzing today, we'll be using two main troubleshooting tools, alarms and wavelength tracker. This is because a channel issue impacting two specific services has been reported. They are no longer working and were functioning normally before a maintenance activity was done against node 1. The suspicion is that something physical happened to the node. This excludes possible bugs or discrepancies with the network design. Additionally, performance monitoring seems to be useless because the affected channels were working perfectly before, and thus everything seems to point to physical damage around node 1. This is the network topology where the technical issue has been raised. It's a 3-node network based on classical ROADM nodes. This means that it's based on classical wavelength router cards and not on the CDCF technology. Let us connect to the 3 nodes to analyze them. Here, we have the 3 nodes as web user interfaces. Let's take the first one and see which alarms are present. We have a loss of signal against 2 transponders, which is compatible with the issue reported by our final user. 2 channels are down, and we need to understand why. Note that no other alarms are present, neither related to these 2 channels nor related to other channels. Let's check the other 2 nodes. As you can see, both nodes 2 and 3 are alarm-free. Let us select one of these 2 affected channels to retrieve the relevant wavelength tracker data in both directions. As we can see, both frequencies 9360 and 9370 are affected. Let's focus on the first, 9360. This direction seems to be clean. All expected data is measured and is within the expected optical power levels. Let us open the opposite direction, that is, Z to A. While the network power trace in the A to Z direction reports optical power levels at each decoding point, the Z to A direction shows that there is a problem. The last endpoint does not detect any optical power. However, it's not so easy to detect the affected fiber jumper, as both the ITLU and the SFD44 are passive boards, unable to detect any wavelength tracker data. Since the channel is detected at the WR888AF level, the issue must be located between this card and the transponder. Thus, the possible broken fiber jumpers are A. Between the WR slot 18 and the interleaver slot 31, or B. Between the interleaver slot 31 and the SFD slot 32-1, or C. Between the SFD slot 32-1 and the transponder slot 2-16. So how do we select the most appropriate fiber jumper to be inspected or replaced? To isolate the faulty location, it's essential to correlate the issue with other channels, which allows us to understand whether the problem affects one signal channel, and in such a case, the culprit could be the only non-shared fiber that connects the SFD to the transponder. Or whether the problem affects also other channels, and in such a case, depending on the findings, the culprit could be a shared fiber, like the one connecting the WR to the interleaver, or the one connecting the interleaver to the SFD. Let us start with checking all channels crossing the fiber between WR8-1-8 dropout interface and the interleaver in node 1. Besides the two affected channels, channel 9365 is also crossing the WR8 interface without being alarmed. Let's check the network power trace of the not affected channel for the same direction, Z to A. As you can see, this channel goes towards another SFD. That is, it doesn't go towards the SFD in slot 32-1, but goes towards the SFD slot in 31-1. This excludes one of our three possible candidates for inspection: the link between the WR card and the interleaver used by the three channels. At the same time, the issue is most likely due to the only fiber shared between channels 9360 and 9370, the one connecting the interleaver with their SFD, as shown in this image taken from the optical network design. Let's now summarize what we have seen in this video. 1. Several techniques are available for troubleshooting: the support portal, comparison between actual and design configurations, alarms, conditions, logs, wavelength tracker, and performance monitoring. 2. Depending on the issue, one or more than one could be necessary. 3. In this specific example, we used alarms and wavelength tracker, as well as a final check with the network design view to locate the shared fiber between the two affected channels. 4. When an issue affects some channels, but others are working fine, we should think about the most probable point of failure, considering that some fibers are in common among multiple channels. Thanks for watching, and look for more videos in our Optical Networking Learning Essentials series. Whether your goal is to enhance your optical networking skills or demonstrate your expertise through one of 4 industry-recognized certifications, the Optical Network Certification Program is here to get you, your career, and your organization on the right path. Our program features 10 instructor-led courses developed by our team of subject matter experts using industry best practices, use case-driven examples, and hands-on labs. Learn more and get started today by visiting our website. Thank you.